This morning, we're really privileged to have with us Dr. Dan Werthimer. Dan is sort of a guiding light in the exascale radio astronomy community, which I think all of us understand is a bellwether for the kind of problems that we try to address here in the OpenFabrics Alliance. So we're really incredibly privileged to have Dan here with us this morning to come talk to us. By pure happenstance and serendipitous circumstance, there's a conference happening a mile and a half down the road at the Hyatt where the world's leading lights in exascale radio astronomy have gathered for their conference this week. So we managed to pry Dan loose for an hour or so to come talk to us. We really asked him for two topics. One was sort of an introduction to exascale radio astronomy, and I think if he succeeds at that, which I'm sure he will because I've seen him do this before, we'll walk away with a pretty clear understanding that they've got the same kinds of problems that we're trying to solve in spades. So if nothing else, if we can create a connection between what's going on in exascale radio astronomy and the problems that they're solving and us, we will have been successful over the past 3 days. I'd go that far. The other thing that we asked him to talk about was correlation. And I don't know anything about radio astronomy at all other than what Dan has taught me off and on. But if you think about, it used to be that these giant dishes, and that was one class of problem. Nowadays, they have arrays of lots and lots and lots of little dishes. You see these pictures all over the place. Correlation is essentially the process of focusing the image from all those beams and creating something usable out of it. So it's sort of a micro look at the real problem from a very low level. So we'll ask Dan to talk about both of those. He's co-founder and chief scientist at SETI at Home, which I guess maybe we could describe as the most embarrassing parallel problem ever, at least in some sense. As principal investigator for the collaboration, I got to get this right because it's hard for me, the Collaboration for Astronomy, Signal Processing, and Electronics Research, known as CASPER, and Dan hides at University of California at Berkeley. Dan?
Thank you.
Don't worry about the purple thing, it won't fly.
Okay, thank you. Thanks very much. So I want to try to give you a little bit of background about how radio telescopes work, and I hope that you'll see that we really need your help. We're trying to process maybe 100 terabits per second of real-time data, and maybe up to a petabit per second, and we need a lot of computing. But I think specifically for this crowd, we are trying to figure out how to connect all these telescopes together, and there's a lot of sort of crossbar switching fabric that we need to learn about from you guys. There's a lot of networking in here, and we astronomers know very little about how to do that. I'm hoping that some of you will get interested in these problems that we have and help us. There may not be a lot of money in it for you, but there are some Nobel Prizes. We're planning to discover gravity waves, find extraterrestrial intelligence, and I'll tell you about some of the interesting problems that we're working on that maybe you can help us with. So let's see. So I want to start by talking a little bit about these problems where you have low data rates coming from your telescope, in which case you can record the data and process it later, this embarrassingly parallel stuff. I'm going to go through that quickly because I don't think it's very interesting for this crowd. But I'm going to concentrate on when you have extremely high data rates coming from these arrays with maybe thousands of telescopes, and where you can't possibly record the data and then bring it to a supercomputer. You have to process it in situ, in real time, at the telescope. And I think that's a problem that you guys could really help us out on. But let me do the first problem first, and I'll just spend a few slides on this. So when you have very low data rates, then we record the data, and one of the things we've been working on, we developed an infrastructure for volunteer computing. It's called BOINC, Berkeley Open Infrastructure for Network Computing. And we take the data from the world's largest telescope, the Arecibo dish in Puerto Rico. You might have seen it in the movie Contact with Jodie Foster, a book written by Carl Sagan, or you might have seen it in GoldenEye, James Bond movie. In GoldenEye, it comes up out of the water, the dish comes up. It doesn't really do that. And in GoldenEye, the dish is in Cuba, but it's really in Puerto Rico. But anyway, that dish is 1,000 feet across. It holds 10 billion bowls of cornflakes. We haven't actually tried that. But anyway, so we take the data from that dish, we record it, and then we break it up into little chunks, and everybody gets a different chunk of the sky. So you'll get one piece of the sky. Everybody, you download the screensaver program. you get 100 seconds of data. And these are our collaborators at Berkeley. These are some of the students that have written the code. It's a big open source project. And we get some help from. So we start with this telescope here. That's the Arecibo telescope I was telling you about. We have about a petabyte of data that we've recorded. We store it at NERSC, National Energy Supercomputing Center. And then we break it up into work units and send it out to the volunteers. And the volunteers run this little screensaver program, which you download one of these little chunks of data, and it takes a long time to analyze it. So this is a lot of computing per bit. So we don't need a lot of help of your network help for this kind of stuff. Anyway, there's 8 million people that have downloaded the thing in 200 countries, and it's formed one of the biggest supercomputers on the planet. And if you add up all the people who are participating in BOINC, not just doing SETI at home, but they're doing a lot of different, I think it is the biggest supercomputer on the planet. And this has led to some bizarre behavior. Nerds like you guys building clusters in their basements. You can go to this website, setifarm.org, and you can see these guys. By the way, they're all guys. And this he's built a SETI cluster, and he's got these bolt cutters. I don't know why he's got those things. Anyway, now there's about 100 different projects that use our software to do volunteer computing. And you can allocate how you want your computer to be used. So you can have 30% of your spare computing cycles for malaria drug research or cancer drug research or HIV drugs or climate modeling. And you can pick your favorite projects and allocate your spare computing time. SETI at home, climate prediction, global warming, gravity wave research, Einstein at home, protein folding. Anyway, there's a lot of different screens. And the idea is, I think you guys are experts at this, that there's about 1 billion machines. This is called edge resource aggregation. There's about 1 billion machines out at the edges of the internet. And so most of the computing power is out at the edges of the internet, of the network. And there's also a lot of storage out of the edges of the network. We recently ported this thing to cell phones. It's now working on Android phones. So you can, I don't recommend you run it except when your phone is charging, but at night, then you can help us find ET. Download the screensaver on your Android phone. And we also have a project called Thinking at Home. This is for stuff that computers are not very good at, but your eyes and brains are good at. We sent this spacecraft out near Jupiter to collect little microscopic particles of dust. In order to find these microscopic particles, we would have needed thousands of students looking through microscopes. Instead, we sent out these pictures out to volunteers to help us find the little particles of dust so we can find how the planet's formed. And we got about 80,000 volunteers. And so now there's a lot of these citizen science projects as well for things that computers are not good at, but people are. But what I really want to talk to you about is this other kind of problem that radio astronomers have, where you can't possibly record the data and process it later. You have to process it in situ at the telescope. We have very large data rates. I think you guys are really good at that. We formed a big collaboration. Unfortunately, we don't have many computer scientists in this collaboration. These are mostly astronomers and engineers, but we have very few people that know about networks and moving data around, and that's why it'd be good to engage some of you. Anyway, this collaboration, which has about 800 people in it at various institutions and labs, it's called CASPER. It's a collaboration for radio astronomy, signal processing, electronics research. And it's trying to solve some of these problems. Here's some of the key collaborators. The problems that we have are, as Paul mentioned, that we're building these arrays of telescope. These are some of the new arrays that we're building. It used to be that we'd build these kind of single dish telescopes, like the Arecibo dish is a single dish. That's a much easier problem. You just have one source of data, one receiver. But with these arrays, some of these arrays have thousands of telescopes, so we have to bring the data together and analyze it. This is one that we're building now in South Africa. You tend to put these things away from people because people have cell phones and transmitters. So this is being built in a desert in South Africa it's very hot and dry and nobody lives there. So it's far away from transmitters. Anyway, so this is one of the telescope arrays that we're building over the next couple of years. Another kind of problem that we have is that the receivers themselves are putting out more and more data. This is an example of a receiver that can put out frequencies between 1 and 15 gigahertz simultaneously, so we can cover the electromagnetic spectrum instantaneously. And so that puts out a couple hundred gigabits per second if we were to digitize that full band. And some of these arrays have hundreds of these receivers. So each one of these things has a couple hundred gigabits coming from it, and we might have hundreds, eventually thousands of these things. So we have a huge amount of data coming from these new receivers, these wideband receivers. Another thing that astronomers have been working on that cranks out a huge amount of data is radio cameras. This thing is called a phased array feed. So most radio telescopes, they have a single receiver at the focus. So they're just looking at one place on the sky, a single pixel. But this thing can look at a whole bunch of pixels at once. So this thing you put at the focus of one of these dishes, and it needs, so now we can look at 64 places on the sky simultaneously. So it's not as good as like a CCD, but we're getting to the place where we can look at more and more. The problem is this thing puts out about a petabit per second of data. So each one of those pixels is cranking out a huge amount of data, and we've got to figure out how to analyze that data. This is kind of very exploratory. We're just trying to figure out how to do this. So the grand vision for radio astronomy is something called the Square Kilometer Array. This is a $2 billion project that is going to be built mostly in South Africa, but also in Australia. About half of it goes in Australia. Australia also has a desert that nobody lives in, Anyway, so this thing is going to be composed of thousands of these dishes, and here you're seeing a close-up, but some of these dishes are in different countries, so we want to spread the array out all over the place. So there's this dense core that's within maybe all the telescopes within 100 miles of each other, but there are also telescopes that are thousands of miles away. So we have to bring data from different we have fibers coming in from all over the place. So this thing is going to produce very high data rates. The whole project is about $2 billion. We're planning to spend about $300 million on computing and signal processing, and we're planning to spend about $100 million on networking, just bringing routing the signals around. So we could use your help on that. This is a plot of the cost of this Square Kilometer Array. So by the way, you probably figured out that instead of building these big dishes, kind of the trend now is to build a big dish out of lots of little dishes. And the reason we're doing that is because it's actually cheaper to build, for the equivalent collecting area, it's cheaper to build a telescope now out of lots of little dishes than big things. The cost of a telescope almost goes up as the cost of the cube, because even though the telescope, we care about the surface, there's a lot of support structure underneath it. And so if you want, just for collecting area, you'd want to build it out of small dishes. You can stamp them out like hot tubs. But the problem is the cost of the computing goes up with the square of the number of dishes. So this is the total cost of the Square Kilometer Array as a function of dish diameter. And so what happens is if you make it out of small dishes, the steel cost, the thing in blue, the antenna cost is very low because you can really stamp these things out, make them very cheap. But the computing costs and the network costs go way up. Those things go up as the square. Well, the computing goes as the square. And so we'd like to figure out how to get that cost down. And I think what's going to happen, the future of radio astronomy is going to be, the Moore's law, steel cost is not going to come down, but computing costs and networking cost is going to come down. So we're going to be building these things out of smaller and smaller dishes, and eventually maybe we'll have 1 million dishes if you guys can figure out how to do that. So right now the cost minimum is around 10 or 12 meters. It turns out if you're a scientist, you'd like to build it out of lots of little dishes. The science is better if we could figure out how to build lots of little dishes. So if you guys can figure out how to get the cost of networking and computing down, that would improve our science. We could look at a much bigger piece of the sky. The yellow, this is the correlator, and I'm going to describe what a correlator is, but that's the thing that goes, the computation goes as the square of the number of dishes. So a correlator is a thing that multiplies every antenna pair. So if you have 3 antennas, you have to multiply A times B, B times C, and A times C. So it quickly kind of goes as you can see how it goes as the square of the number of antennas. And so that's why that thing goes up kind of rapidly as you go to smaller antennas. So that computation goes as a square. The networking, I think, is shown, it's not really dominant in these things. The computing is the brown thing. The data rates are linear with the number of dishes, but the computing goes as the square of the number of dishes. The other kind of thing we're working on that I think networking is going to be a big deal is how to do multiple experiments simultaneously. So we want to do take the data from these telescopes and split it, perhaps with a multicast switch, into lots of different computing elements. So we can search for pulsars, we can map the galaxy, we can look for ET, we can do different experiments at once. And I think you guys are expert at kind of this multicast stuff. Traditionally, this has been done where you take the data and you split it with analog splitters, and you split the voltages up, and then each instrument would digitize it separately. But I think we're going to try to learn how to do this experiment where we digitize the data once and then split the data digitally, perhaps in a multicast switch, or maybe you guys can give us advice about how to do that. And we want to try to figure out how to have this kind of, a lot of computing hardware out here that's kind of dynamically allocatable so that different astronomers can allocate it different ways. But the idea is we want to be able to do different things with the data simultaneously and route it to different computing resources. The computing resources over here, they might be very specialized things, ASICs or FPGAs or whatever you guys got, or they might be general purpose sort of x86 or ARM boxes or whatever you guys recommend that we put there, or probably some kind of combination of specialized processors along with general purpose processors.
I think we're still shaking our head over terabit multicast.
Okay. Well, we could start small. I think it'd be nice that if you can just help us with the architectures and then teach us how to scale it up. So the kind of technologies that we've been playing with for computing technologies are CPUs and clusters of CPUs and clusters of GPUs and clusters of FPGAs. And we've also been working on ASICs for some of this very specialized computing. It turns out some of the computing in radio astronomy is like incredibly simple algorithms. And also we can get by with a small number of bits sometimes. We're trying to add trillions of samples together, and our samples are just noise. If you listen to radio telescopes, it's just that static. In fact, if you the old televisions before HDTV, if you turn on your TV between the channels and you saw that static on the screen, that white stuff, some of that was from the Big Bang radiation from 13 billion years ago. Some of that static that you see on your TV is coming from the Big Bang. But it's all just noise. But in order to find the signals buried in the noise, we want to add trillions of signals together. But because it's noise-like, we can get by with very small number of bits, 3-4-bit computations. And that's one of the things that we'd like to get some advice about, how to just do these small number of bit computations. We use FPGAs and GPUs. I think a lot of you are experts at these kind of technologies and what the pros and cons are. We find that GPUs are a lot easier to program than FPGAs. But we're having a problem getting the data into the GPU. So we typically, these new GPUs from NVIDIA or AMD have thousands of cores, and they can do several teraflops. And oftentimes the bottleneck is just the I/O from getting the data in, typically on 10 or 40 gigabit Ethernet, through the NIC card, onto the motherboard, into the GPU. And the way we're doing it now, I know you guys know how to do it better, but the way we're doing it now is we're doing 3 transfers to get it into the GPU. That's getting it from the NIC card into kernel memory, and then getting it from kernel memory into application memory, and then we transfer it from application memory into the GPU. And that's all silly, and I know you guys know how to do it better with RDMA, and I think it'd be a really cool project if you can help us figure out how to do that faster. Traditionally, astronomers have been building very specialized hardware for these correlators and beamformers. They build kind of specialized boards, and they tend to make the boards really big. This is a board with custom ASICs. And the reason that we've done it before with really big boards is because The big problem is interconnect. And so the bigger you make the boards, the more stuff you can put on the boards, they minimize the interconnect problem. And I think that you guys know how to solve these interconnect problems. But typically you build really big boards, kind of custom boards, and then you have custom kind of backplanes and protocols and custom chassis. And this is the kind of thing we're trying to get around. And I think what we want to move toward is kind of industry standard interconnect. You know, we want to have 10 gig, 40 gig, whatever you guys recommend, maybe InfiniBand. And we're trying to do, instead of specialized hardware, we're trying to get kind of general purpose hardware. It might have FPGAs or ASICs on it, but we want to make it look like a computer. We want to make it look like it's running Linux, and we want to make it talk over Ethernet or InfiniBand. And our collaboration is developing open source hardware and open source software and open source gateware, and I think it fits very nicely into your kind of open source community. And we have, if you're interested in this stuff, you can subscribe to our mailing list and come to our workshop, and I'll tell you about that later, but we have an annual workshop where everybody comes together and talks about the problems and what they're working on. And the next one's in June in Berkeley, and it'd be great to get some of you there. We have talks in the morning, and then we break up into working groups and laboratories in the afternoon. So this some of our hardware. There's nothing weird about our hardware except that we've decided that all the hardware should talk Ethernet. This one's got 18 10 gig connections on it, a bunch of FPGAs. This one is kind of a newer thing. We're trying to make it now look more like a computer. We put it in a pizza box to try to convince people that we're doing kind of computing. This is a big FPGA, and there's a little processor on there to run Linux. And we make the FPGA code run like Linux. So you get a Linux prompt, and you can submit your job, and it'll find FPGA that's free and submit your job to the FPGA, and the I/O is done through Linux files. So we're trying to make FPGA computing look more like sort of inside Linux. So we've modified the Linux kernel to run these FPGAs. Anyway, these are high-speed ADCs, so you can bring in your analog data, digitize it. What comes out of these things are a bunch of 10 gigabit Ethernet ports. And so you connect a whole bunch of these things together. There's a bunch of analog digital converters to digitize data. These are all open source boards. And I think I told you we're trying to get around these backplanes. But you should tell me if this is wrong, but I've been around a long time, and I remember some of these buses. Some of you have been around. And the buses, these backplanes seem to last a few years and then they kind of they go extinct. And we think the right way is to use external interconnect to connect all this stuff together and not slide stuff into a backplane because we think it lasts longer. And we're betting on Ethernet, maybe 10, 40, 100 gigabit Ethernet. We're not using InfiniBand or any of this other stuff. But we think Ethernet, but I'd like your advice about this. We think Ethernet's going to be around for a long time. And right now we're using 10, 40 gigabit Ethernet. But my guess is that when 100 is more common or whatever, terabit is more common, there'll still be some box that will allow us to convert from one. I think you can even convert 10 megabit Ethernet from back when I was young to. You can still get it on the net today. Now we got stung a little bit with connectors. Our first boards had these CX4 connectors. I know everybody uses SFP plus or QFP connectors now. So now we have these mezzanine boards that you can put on our FPGA boards that will accommodate different kind of connectors. But I'd like to hear from you about that. Maybe we should move to RJ45 or something like that. I'm not sure what you guys recommend. Anyway, we call it kind of computing by the yard. This is what kind of a system looks like, all the kind of connected all up with 10 gigabit Ethernet. Here's another example of a thing we just deployed to look for ET. And it's sort of on the left are a bunch of FPGAs to digitize the data and get it, timestamp it, and packetize it, get it into a switch, a 10 gigabit Ethernet switch, and on the right is a computing cluster with a bunch of GPUs to analyze that data. We've also been working on ways to make it easy to program FPGA. So FPGAs, some of you may know, are really painful to program. It's like machine language, this HDL, Verilog, VHDL stuff. And so we've been working on high-level languages to make it easy for astronomers to put this stuff together. We use a language called Simulink. It's a graphical programming language, much like LabVIEW. And we have a bunch of little modules that astronomers are used to, like fast Fourier transform modules, polyphase filter banks, digital down converters, correlation blocks. So you don't really, you can make your own modules, but anyway, we have a bunch of these kind of gateware modules and hardware modules, and you kind of stick them together, and we have tutorials about how to build all this stuff. And there's a lot of stuff that people build, spectrometers and correlators, and I'll tell you a little bit about how these things work, beamformers. And I think I'm going to maybe I'll talk a little bit about some of these architectures. So the kind of simple architectures are you digitize data. Maybe you just have a single receiver. That's the kind of simplest thing we do. You digitize data, and it goes into an FPGA. And the FPGA might break it up into different frequency bands. So you're trying to analyze a big chunk of the electromagnetic spectrum, and the FPGA break it up into little chunks, or maybe coarse chunks, and then send each chunk of the band to a different computer cluster or different FPGA board. So it goes into a switch, and the switch routes these packets to different computing elements. And this is the same kind of thing where you digitize data from a single pixel. These are multi-pixel receivers. So now we have a whole bunch of telescopes out here, or feed elements on a single telescope, and we're digitizing data from a bank of these things. And then these things are typically FPGA boards that are doing a little bit of processing to the data, but they're also in charge of getting out of this kind of synchronous world and going into the asynchronous times. So the packets are coming out of here are time-stamped packets in either time domain or frequency domain data, or maybe both. And they're going into a big switch. And then over here, we're having a cluster of CPUs, GPUs, or maybe ASICs or FPGAs to analyze the data. And we typically need, as these things grow, you can see we need bigger and bigger switches, although there are ways to build these things out of a bunch of little switches. But we're interested in big switches with thousands of ports. And typically we need full crossbar, full aggregate bandwidth kind of switches. And I think some of you have a lot of expertise on that, and I'd like to learn about that stuff. For the square kilometer array, we're going to need things with thousands of 40 gigabit ports, full crossbar switches, and I'd like to know what you've got for that sort of thing. This stuff is used in SETI, Search for Extraterrestrial Intelligence. That's my specialty, trying to answer the question, are we alone? This is kind of, in SETI, one of the problems is we don't know what frequency ET might be transmitting on. Let me back up a little bit. In SETI, one of the ideas for answering this question, are we alone, is anybody out there, is that Earthlings are broadcasting radio and television out into space, radar signals, and I Love Lucy left the Earth 50 years ago, has gone past about 10,000 stars, and the nearby stars have seen The Simpsons. And so you can put the question the other way. So we're polluting space with all this radio, television. Maybe if other civilizations are out there, maybe they have something like that we could detect, either that's accidentally leaving their planet, much like television leaves our planet, goes off into space, or if we're very lucky, maybe they're interested in communication, maybe they've seen oxygen or atmosphere, maybe they've seen Ed Sullivan, and they are sending something in our direction, deliberately want to communicate with us. And we'd be happy either way, but the problem is we don't know what channel to listen to, what frequency to listen to. And so you want to listen to as many channels as you want. You want to digitize as broad a bandwidth as you possibly can and break it up into lots of channels. And when I started in this game in the 70s, I was in the Homebrew Computer Club, and everybody in that club got rich, except for me, because and my computer was just as good as the Steve Wozniak was in that club, and he was designing computers, and I was designing computers, and my thing was in many ways better. But anyway, but I was thinking about this stuff to do SETI, and they were thinking about other stuff, so that was my big mistake. But anyway, so anyway, so I made this thing that could listen to 100 channels at once. And that was, everybody thought, wow, that's really cool, because it used to just listen to one channel at once, like tuning your radio, one frequency at a time. And then, so I used the very first computer chips to listen to 100 channels. I wrote some Fourier transform code to do that. And I thought, wow, gee whiz, everybody was very impressed. And then we went to 65,000, then 4 million, and now we're up to 5 billion channels. And that's just, it's not because I got any smarter, it's because people like you kind of figured out how to do computing and networking better. That's really encouraging if that trend continues. Eventually, I think right now, we'd be really lucky to find these signals if they're out there. We're just learning how to do this. We're just scratching the surface. But I think if that trend continues, eventually we will be able to do a thorough job of looking at all the different places in the sky and all the different frequencies and signal types. But right now, we'd be lucky. But if that trend continues with maybe your help, we can find signals if they're out there. We're working on ASICs. We're working on very high frequency telescopes. These are some of the scientific things that we found. We don't know what these things are. There's these things called fast radio bursts. These are explosions. They're only on for 1,000th of a second, a millisecond, and they come from billions of light years away. They're the most energetic things, the most powerful things in the universe, but they're only on for 1,000th of a second, and then they go away, and we never see anything at that place again. And we just discovered them a few years ago, and we're trying to figure out what's going on. Maybe exploding black hole, or we don't know. But we're trying to figure that out, and we discovered that with some of this technology. Got on the front cover of Nature. We made the first maps of the black hole at the center of the galaxy. We found a bunch of stuff. This is one of my students built this little thing, and it's just it's a ADC and a switch and some computers, and she found a planet made out of solid diamond. And my wife wants to know how we're going to get that thing. I don't know the answer. So anyway, if you help us with our networking problems, maybe you can find a planet made out of solid diamond. We also use the same technology that we developed for radio astronomy and SETI in other things besides astronomy, people doing neutron magnetic field imaging. We used it to read out data from a brain. We're working with some medical people who are trying to do prosthetic control where we get the data out of a brain with these neural implants. So I wanted to maybe change gears a little bit and talk a little more specifically about this problem that we have of interconnect. In the biggest problem of interconnect in the radio astronomy signal processing are in these correlators and a little bit in the beamformer. And before I just want to maybe scribble on this pad a little bit so you can kind of see how the interconnect works. So just remember that what a correlator is doing is if you have an array of antennas, radio telescopes, you need to multiply all the possible pairs. So let me draw sort of 3 radio telescopes here. So I need to multiply this pair together. I need to multiply this pair together. And I need to multiply this pair together. Okay? So that's, and you can see that this is kind of a networking problem. It's going to get messy. There's going to be a lot of wires on here as I go to more, and this may be, 1,000 telescopes, or in a square kilometer radius, 4,000 telescopes. So it's going to be a lot of interconnect to do all those cross multiplies in a correlator. So that's kind of one of our biggest networking problems, is to build these correlators. And we could use your help on that. On the beam, so this is a correlator. You can see the code for this is not very complicated. It's really an interconnect problem. A beamformer is a little different. Oh, by the way, the correlator, the networking is going linearly with the number of telescopes, right? The the number of bits per second is just proportional to the number of telescopes I have times the bandwidth of each telescope. Okay? But the computation is going as the square. The beamformer, let me just show you how a beamformer works. Let's have 3 dishes here. So if the light is coming from the star, the radio waves are coming from the star this way, say it's coming down this way from a star off here in this direction. What I have to do is take these 3 signals and add them up. But before I add them, I want to delay them a little bit because it's going to hit this one first, and then it's going to hit this one, then it's going to hit this one. So I want to put a big delay in here, a smaller delay in here, and a really short delay here, and then I can add them up. Okay? And if I put in the right delays, then I'm looking from this direction. But now suppose that I also simultaneously want to look over there. So if there's a star over there, a galaxy over there, the light's coming in this way, it's going to hit this telescope first, and then this, right? So if I want to form that beam, then I take those same 3 signals, but have different delays. So this one now has to have a long delay, and this one has to have a medium delay, and a short delay, and then I add them up, and now I have a new beam from a different place on the sky, right? And I'd like to do that multiple times so I can have multiple beams and look many places on the sky at once. So you can see that that's kind of another kind of networking problem that we have. And maybe you can tell us how to do that as well. Is that all? Everybody got that memorized? Okay. Okay, so that's kind of the fundamentals of these different things that we want to do, form beams and form correlators. So I mentioned this, the operations per second of a correlator is proportional to the bandwidth coming from each antenna times the number of antennas squared. And so if you want to analyze, for instance, the typical number, 3,000 antennas, this is kind of an aggressive number, and a gigahertz of bandwidth, that's a lot of computing. These are complex multiply accumulates. But the data rate is not as bad because it's linear of order terabits per second. Although some of these telescopes now we want to analyze quite a bit more bandwidth. And this is per beam, and sometimes we have 100 beams. So the data rates can get up to petabits. So by the way, these telescopes are really limited by computing. If you can give us higher data rates and more computing, we can survey the sky faster and have a better chance of finding ET. So if you want to read more about correlators, if you're unhappy with these 2 diagrams that I've drawn, here's a couple of references. There are a lot of people working on correlators in our CASPER collaboration. These are some of the groups that are building correlators. So there's a big interest in this. These are the people at Berkeley that are working on this. We've been building correlators for, 40 years. There's different technologies for these correlators. There are different kinds of ways to compute. You can do it in software. Just using kind of x86 boxes. There's some nice open source software called DiffX. And that's good if you have a small number of antennas and a small bandwidth, that, just because that's the easiest thing to do. But as you go to larger number of antennas and larger bandwidth, we have an open source code that runs in GPUs. And we have also code that runs in FPGAs. And we've been working on ASIC correlators as well. We're interested in other platforms. I know some of you are experts at Intel Phi and other kinds of computing platforms, but I'd be interested in talking to you if you've got some ideas for how to build correlators out of different kinds of technologies. So remember, we want to cross multiply we want to multiply every pair of antennas. So this is, if you can do it all on one board, this is what you do. So here's an array of antennas. You make a copy so you have data also going this way. So you have data marching across from, say, let's say you have 50 antennas. So here are the 50 antennas, digitize the data. Here are the same 50 antennas, digitize the data. And at each intersection here, I can cross multiply. So I'm multiplying antenna A by antenna A, but I'm also, the next one is antenna A by antenna B, and so on. And I get all the possible cross multiplies. So you have an array, maybe a systolic array. And that works if you can do it on one board, if you have a small number of antennas and a small bandwidth. The problem is it's hard to build something big over multiple boards with this kind of architecture. So that's what's in a complex multiplier accumulator, is a multiplier and a little vector accumulator, kind of a barrel register. So this is kind of a more general purpose architecture called an FX correlator that's a much more scalable architecture. The thing I just showed you is something you could get by until you kind of run out of space on the board, and then there's no way to sort of scale it up. But this is a way we think that you can make really big correlators. It's called an FX correlator. F is the part where you take its frequency, you break a wideband up into small frequency bands. So what you do here, and X is the part where you cross-correlate. So frequency, break up into frequency bands is the F, and then cross-correlate is the X. And over here, you have what we call the F part of the correlator, and over here we have the X part of the correlator. So what we're doing is we're digitizing the data from a telescope, and then this part is breaking the band up into little chunks of the spectrum. So we channelize the data into different frequency channels. And then what we do is these X parts here that cross-correlate, this guy over here, this X engine, he works on one frequency band, but he has to get data from each telescope. So here's 3 telescopes, A, B, C. He gets the lower frequency band from A, and the lower frequency band from B, and the lower frequency band from C. And now on the band that he's working on that frequency chunk that he's working on, he now has enough information to cross-correlate and do all the different, he can multiply A times B and B times C and A times C from those 3 antennas in his frequency band, right? And then this guy here, he's got a different frequency band to work on, so he gets data from all these antennas, but in a different frequency band, and he can cross-correlate from all the antennas in the frequency band that he's been assigned. And so now in this particular diagram, we've broken up into four frequency bands, but each of these X engines has to get data from each antenna, but not the full data rate from each antenna, right? So this guy gets a quarter of the data from this antenna, a quarter of the data from this antenna, and a quarter of the data from that antenna. Does that make sense? Okay. So we think this is a scalable architecture, but notice we've got a kind of a lot of interconnect here. And also notice that this is dedicated routing. I don't really need a super flexible mesh here that can route anything to anything. Anyway, what we've done, by the way this was done in the past is all these things were wires, and some people had more than 1 million cables in their correlator because of this n squared. This is an n squared routing, right? If you got, it's the number of antennas times the number of X engines is, there's a lot of interconnect going on in here. And so some people ended up building their correlators. Each one of these things was a wire or a cable or a coax cable or something like that. And they had cables that were like a couple yards across of cables of 1 million wires in their correlator. So I think you guys would think of this right away, but it took us a long time to figure this out, is you can replace this interconnect with a switch. And so what you do is you packetize the data, and this guy sends a packet to this X engine, he sends another packet to this one, another packet to this one, and then this guy does the same thing. He sends a packet through the switch to this one. Anyway, it took astronomers maybe 30 years to figure this out. It's actually my group that figured it out, is that we should just buy this thing from what you guys build. and just packetize our data, because this what you guys have. I think you have like an n squared kind of interconnect in here, or maybe it's some kind of levels, lots of level. I don't know how you do it, but somehow you've got this really complicated thing that we've been working on for years, and you already kind of solved that problem in a big switch. So instead of using 1 million wires now, the number of interconnects is more just scaling with the number of telescopes instead of the square by using a switch. But so we kind of shifted the problem into a problem that you guys know how to solve, but that's a good thing, because I think you guys put millions or even billions of dollars into designing these switches, so we kind of shifted to industry so we can buy those things from you guys. Here's another diagram that's very similar. You digitize the data, you squirt it into a switch. There's a big crossbar thing going on in here, and then a bunch of different things. Same idea here, same idea there. We've also been working on the data transport codes to move high-speed data from NIC cards. I think I mentioned this before. So we have this problem of getting data from a NIC through the CPU into the GPU and on the disk. That took a lot of work. You'd think that's really simple, just moving data around. Maybe it would have been if you guys did it, but it took us a long time to figure out how to move these high-speed data around through all these circular buffers and make. We typically use these computers with a couple of different PCI buses and dual socket machines, and we can get about maybe 40, 50 gigabits per second from the outside world into these GPUs doing that. We'd like to get more. I think I showed you a lot of this stuff. I think I'm going to skip some of these details of how the F engine works and the X engine works. These are some of the things we've been building with these big correlators. This is an antenna array with 256 of these weird low-frequency antennas. And this is to try to figure out how the very first stars and galaxies formed, which was about 13 billion years ago. The universe is stretched by a lot. And so what used to be short wavelengths are now these long wavelengths, and we can use these long wavelength antennas because it's stretched in those 13 billion years. And anyway, we just built this thing. This is working in Southern California. We have another one in South Africa. And this is one of those Nobel Prizes that I was telling you about, that if you help us build this thing, you can share. Although only 3 people get the Nobel Prize, but we're trying to fix that. This is our next generation thing that we want to do. And we don't really know how to do that. The place where we're going to put the correlator is over here. It's about 10 kilometers away. And we have to figure out how to get the data from this thing over to the building here where all the GPUs and stuff is. This is the same building where they're building the Square Kilometer Array in South Africa. And they built a huge underground bunker, and it's got 1,000 equipment racks, now mostly empty. And we're starting to populate that now. And this is the first dish that we're going to build. It's being led by Berkeley, by our group. And we don't really know exactly how we're going to get the data back from here to the correlator. Maybe you guys can give us advice. But what we're thinking is we're going to maybe take a little cluster of three or 4, or maybe 8 antennas, and we're going to have a little station there where we digitize the data locally at that little batch of antennas, and we're going to get the data into Ethernet, maybe 10 or 40 gigabit Ethernet. And then we're thinking that at that station we will transmit the data on different colored lasers, these little, CDMA, what's it called, CWDM or DWDM, we're not quite sure what, to just minimize the number of fibers if we have different colored lasers bringing the data back over Ethernet. And we're kind of struggling with that a little bit. We don't know very much about DWDM or CWDM. If any of you know about that kind of stuff, I'd like to talk to you and try to figure out how to get the data back from all these telescopes to our central building. And then in the central building, there'll be a big switch to interconnect it all and do that big crossbar thing to do the cross correlation. And we'd like to talk to you about that too. This is the very first correlator, a digital correlator that was built in 1960. It had 21 frequency channels. The clock frequency was 300 kilohertz. And the correlating processing power has been going up with a nice kind of Moore's law. This is a log axis. Unfortunately, correlator salaries, the engineers that design these things and has not gone up by a similar factor. So even though correlator performance has gone up by a factor of 1 million, our salaries have not gone up by a factor of 1 million. We'd like to fix that. If any of you know how to fix that, I'd like to talk to you. Anyway, there's a lot of these different correlator projects going on, and we'd love to get involved, get you guys involved. The communities, the Collaboration for Astronomy, Signal Processing, Electronics Research, CASPER. You can find us on the website, just Google CASPER, and you can join our mailing list and come to our workshop. We have a little joke, CASPER the Friendly Ghost, where GHOST is group, helping open source signal processing technology. If you want to get into this, we have these little tutorials where you build a spectrometer, you build a correlator, you do a little heterogeneous computing, combining these FPGAs with GPUs and CPUs, and you learn a little bit about how to program in Simulink and HDL. And these are things that our undergraduate astronomy students learn how to do. They all take a little 1-week workshop and they build this stuff. And if you come to our workshop in June in Berkeley, we'll have talks in the morning, and in the afternoon we have these working groups, but we also have a little lab set up, and you can help us build this stuff and find out where the bottlenecks are and help us improve it. And so this is the invitation to this workshop, and it's going to be in June, and I hope some of you can come, and it'd be great if you can give us talks about the kind of stuff that you're working on in networking, because we really need to learn about that. Thank you.
Yeah. Question. You mentioned a couple of large arrays, and I noticed they're both in the southern hemisphere. Are there any large arrays in the northern hemisphere?
Well, not really big ones. The big ones tend to be in the south. The money's going in the south now because the south has been largely ignored. There's a lot of interesting stuff. The galactic center's down there. Also, it turns out that the north has a lot of people in it, and we want to get these things far away from people.
You don't want it to be really cold, at least.
Yeah.
Okay.
We may eventually have to put these things on the backside of the moon, where the moon would act as a shield from all the pollution that you guys are generating. And
hard to get a fiber there.
Right. Maybe you guys can figure out how to do that. And anyway, this may be a kind of a unique opportunity to look for other civilizations and do all this other stuff, where we don't have to have this incredibly expensive thing on the backside of the moon.
And only half the galaxy, at least, right?
Yeah. These telescopes can typically, if you have a fully steerable dish, you can see about 2/3 of the sky. But you're right. We'd really like to have one in the north and one in the south. If you write us a check for another $2 billion, we'll put one in each place. Yeah.
So when you mentioned the lasers, it seems like I kind of remember reading, isn't this like the same? Have y'all looked at what the high-speed trading companies are doing with, they buy these laser antennas that will be like downtown New York and some data over New Jersey. Maybe, I know there are companies that sell these lasers transmitter things to those kind of problems.
Yeah, so actually the modules that I was thinking of are these little SFP plus transceivers that you slide into your 10 or 40 gigabit Ethernet port, and they have different colored lasers built in. They're made by companies like Finisar, and it looks very similar to like an Ethernet cable, but in that little module that you slide in, that SFP plus module, they make them with different colored lasers. I think you can get them with like 100 different colors.
Yeah, he's talking about over the air.
Yeah. You're saying instead of burying the fiber, we should transmit the data open air links. Free space lasers. Yeah. That's actually a cool idea because it's kind of expensive to bury this fiber. And so, we need a few terabits per second, but maybe we should do that. Yeah, I'd like to explore that. I don't know. Yeah. So we were thinking, but maybe this is wrong, but we were thinking we'd do the kind of more conventional stuff where you bury a bundle of fibers, an armored jacket. I don't know much about that, but the open air links would be good, and they don't interfere with our radio stuff. And I don't think it rains there.
They do have passive optical splitters that,
Yeah.
actually there's somebody here that sells those, but, yeah, you can get the fiber run. They've got passive, doesn't even take any electronics.
Yeah.
And you run 8 or 9 of these things in, and it's actually passive.
Right. I've seen the passive multiplexers and demultiplexers for the multiple color CWDM and DWDM stuff. And that's the kind of technology we're thinking of. But we don't have much experience with it. We'd like, if any of you are experts at it, I'd like to get advice.
They sell them, make them.
Okay, good. Yeah, I'd like to talk to you. See me after class, please. Okay, well, thanks very much.